Okay, so today it's about something called discrepancy. Let me skip all this stuff. Um, I had this idea once that like if I made summary slides for everything, it would make everything feel more coherent. I mean, by now it's just like okay, all right, okay. So we're looking at like an example would be something like balanced coloring. Okay, so I have points and sets, and I want to color them red or blue, and I want to make them as close to even as possible. Yeah, maybe you have some theory about elections and this will empower everyone's vote more. I don't know. But actually, that would be drawing sets around colored points, probably. That's a little different. Okay, so your goal is to take these points and try to color them, and you want in every set the number of red points to be as close to the number of blue points as possible. So you're going to pay the difference in absolute value. Okay, you want to minimize this quantity um, over all possible colorings. If you want, you can think of this as like a plus one or a minus one, and then it's just the absolute total. All right, so is it worth coloring this together? No, okay. S so here with the an example. What is the discrepancy of this coloring? So you want to find the worst set in terms of the difference. Is it even? Uh, are they all even? I could have essentially done that. Yeah. Okay. Yeah, it's probably pretty rigged because when you're making these examples, you can just add dots to fix things. Okay, so this would be something with discrepancy 0. So this is ideal. Okay. Now, okay. So, well, okay. Any ideas for trying to compute discrepancy? I mean, a minimum discrepancy coloring. Yeah. All right. So maybe a natural first idea is uniformly random. So if you did a uniformly random coloring, let's say you have n sets and n points, what kind of discrepancy guarantee can you get? Okay, y square root n. All right. So let's just fix one set S that has like n, up to n points in it, right? So, and then what we can do is we can, create random variables. Let's say that there's L points or L is less than or equal to n, right? And we're doing a random coloring. So these will be like plus or minus one. Plus is like red, minus one is blue. Okay. And so your sum, xi will, the absolute value of this thing will be your discrepancy. Okay. And your expectation would be, sorry, the expected sum. Well, same as individual. What's expected sum? The expectation is going to be 0, right? Plus one, minus one, half and half. Okay, but that's different than like the expected absolute value and stuff like this. So how can I try to analyze the absolute value over this kind of simple experiment? The variance is like n over 4. Yes. Now you could potentially do better because the xi's are completely independent. Yeah. Yeah, we can use a turn-off bound. Now, one thing I want to point out is that more often than not, we've done the multiplicative turn-off bound, where you're adding a bunch of non-negative things towards a big positive average, and you're trying to get off by some percentage of that average, right? So everything's in this positive thing, like trying to get 5% error on 0 doesn't make sense, right? So here we're going to use that additive version, which only kind of, I think for us, only showed up in VC dimension, but it's always been there. It's just not as common for us in CS. Okay. And I have it here on the right. Okay. So 0, 1 could have just as well been negative 1, 1. That's not a big deal. But it says, okay, the odds that the average is bigger than, sorry, the empirical average is bigger than the expected average plus something is less than equal to e to the negative something squared times n. Okay, so how would that apply for us here? So suppose I want to analyze, the probability that, and we'll figure out kind of the right value of lambda. What are the odds that for a particular set, uh, the discrepancy is at least lambda? Yeah. Yeah, yeah, yeah. Okay, so yeah, I could put absolute values around both of these, and then there'll be a factor two in front, so that's fine. So yeah, that's true. We only have to worry about greater than equal to, and then the other side will follow. Okay, so let's say I'm just doing greater than equal. So okay, if I plug in this Chernoff bound, I'll zoom in for us. You need some epsilon squared n and stuff, right? So what does that become for us? Lambda? Uh, yeah, I'm sure there's a constant negative two lambda squared. Yeah, so I think this will be an over n if you want to apply it directly. So divided by n squared times n. Okay. So you get something like, I'll put the absolute value back in, put a 2 here or something, e to the negative lambda squared n. That's right, divided by n. Okay, good. So that's just for one of these, right? This is just from plus or minus ones being independent. This is a standard Chernoff bound kind of thing. So now, how can I try to how I want to make lambda small, right? As lambda gets big, this thing drops off. But how small can I make lambda? Remember, I want to make sure that all the sets get some discrepancy, not just one. How small can I make lambda? One. So if I put one here, I'll get e to the negative one over n or something. So it's probably very close to, that's not a we want this whole probability to be small, right? Because this is the odds of my discrepancy being bigger than my target lambda. Root n log n, why? All right, root n log n, throw some constant in front, okay? Then you're going to get something like e to the, 1 over, well, I'll do it slowly, e to, some constant times log n. So the square root log n gets squared. Log n, and then we get our favorite, 1 over some polynomial n. Okay? And in particular, that's small enough to let you union bound over all the sets. Okay? So a naive coloring is going to get you square root n log n by applying the additive Chernoff kind of in a straightforward fashion and then taking a union bound. Okay, that's what you need for a union bound argument. Okay, so in 1985, Spencer actually taught me algebra, came up with a better bound. Anyone want to guess? Root n. So he showed that you can get something on the order, I should have put order up above too, but on the order of root n. Some level basically doing better than the union bound, or kind of removing the union bound cost. Yeah, this is like a game that we play, which is like obsessing over removing the extra log factor, but this is another one of those. VC dimension is another situation where we were so excited to remove a log factor. Okay, and slightly more generally, if those m sets and endpoints, you can get root log m over n instead of root log m, which is normally what you would need to union bound. Okay, so for m equals n, you get this thing. Okay, the proof was existential in nature, and so it was a big question in 1985, or since 1985, as to whether you can get an algorithm for it. It was sort of like in the same status as like the Lovat's local lemma. Yeah, and Spencer, I think, would actually go around claiming this is an example of something that could never get converted into an algorithm. Yeah. Oh, okay. I mean, there's sort of like a hidden, it should be like 1 plus m over n. Yeah. Okay. Or 2 plus, yeah. Okay. So that's where at some point the CS people get excited. I mean, we all read this math book that has this famous result in it, the probabilistic method. And okay, so this is somewhat recent. So Nikhil Bansal in 2010 was able to get an algorithmic result. Okay. And his was based on kind of rounding semi-definite programs, which we didn't do so much in this class, but it's sort of like an LP on high dimensional steroids. And so he was able to get this root n times log m over n type of bound. So at least when m is equal to n, he was able to recover the kind of famous square root n bound. Okay. And then a follow-up paper a couple years later uh, was able to get root n log m over and fully get the general case. But one thing also is that the algorithm is like I think very pretty. It's very simple in some sense from a certain perspective, and so that's what we're going to talk about today because it's some kind of yeah, you can argue it's like kind of a simple natural random walk, and it just does what you want. Okay, I'll try my best to illustrate that. Might not seem simple because there's like some calculations involved, but actually the algorithm itself is kind of simple. Okay, so that's what we want to prove. We want to analyze the square root n log m over n result. Maybe before discussing the algorithm, I could still solicit any suggestions for doing better beyond kind of naive random coloring. Any ideas? Just curious to see if anyone comes up with anything. Can you convert it to an LP and try to round that? Well, the LP could put 1/2 everywhere. The LP is going to put 1/2 on all the colors, right? Because that'll just get, yes, I think that's one thing to point out, right? So if you did a linear relaxation where I can add fractional colors, I would just do half and half. And then you just get discrepancy 0 everywhere. And if you did like, I mean, a straightforward way to round it would probably take something of half and half and then do 1/2 red, 1/2 blue, and we'll just come back to what we just did. Okay, so yeah, LP rounding won't help. Yeah. Well, it definitely wouldn't, but I'm trying to think of a counterexample. Uh, yeah, so I don't think greedy will work. But yeah, it's a standard suggestion. I just can't think of a good. Why? Um, how? Yeah, first we have to imagine greedy, right? So maybe you pick a random point to color, and you just keep trying to balance it. Okay, and trying to balance that. Okay, yeah. Can you kind of try to do one set at a time? So I can pick a set. Maybe I can take the biggest set because that seems dangerous, or a set that intersects a lot of things. Um, yeah. I mean, it feels a little bit like SAT, where okay, focusing on one set is at the neglect of other sets, and also weird connections across sets. It's not clear. What you're committing to when you color one set. You could maybe take under consideration at least the immediately overlapping sets, but you can imagine like a big long chain of sets where one mistake here really propagates out to a chain of overlapping sets. Yeah. So anyway, but it's still fun to think about. All right. So okay. So like I said, it's going to be some kind of high dimensional random walk. Okay. And we're going to abstract out kind of the picture of sets. So there's going to be n coordinates that represent the endpoints you want to color. And you have these m sets, they're all subsets of n. Okay. And you want to effectively assign -1 or +1 to every point. So you can think of that as picking a vector that's sort of like on a hypercube. -1 or 1 is these corners. Okay. And I'll say like for a set S, x of s will just sum up the coordinates inside. Okay, so absolute value of x of s will be the discrepancy for that set S when x is all plus and minus ones. Okay. All right. So that's just some notational setup. And so what we're going to do is we are going to at least take a continuous point of view. Okay, so we're going to try to do fractional colorings, -1, 1. We can start at all 0, which is like, no discrepancy, right? So it's a perfect solution in some ways. It's just nowhere near, kind of a fully integral coloring. So you can think of this as also like you can think of this as almost rounding an LP, where in this particular case, solving the LP is trivial because you start at the all 0 solution and you want to gradually turn it into a 1 or -1 solution. Okay, so somehow it's still got this flavor where we're trying to make it integral, but the way we're going to make it integral is quite different than what we've previously seen. So we're now when we do a fractional coloring, what we're going to do is we're going to make small changes to all the coordinates xi, and we're going to hope that they get very close to 1 or -1. Okay, and as you make lots of little random changes, you might imagine situation things get kind of delicate when you get very close to 1 because you don't want to exceed 1 and you don't want to go below -1. Okay, so what we're going to do is take epsilon to be like 1 over n, something very small. And I'll just say once the coordinate is at least 1 minus epsilon, it's sort of done. It's frozen. And otherwise, as long as it's sort of padded away from -1 and 1, it's still kind of alive and free. Okay, so this is like a minor thing. This is not a big deal, right? If I have a sort of a tight fractional coloring, so everything is very close to 1 or -1, but it's not exactly 1 or -1, I can convert it into exactly 1 or -1. Why? How? Yeah, so if you just, take everything that's at least 0.99999, turn it into 1, and below -0.9999 turn it to -1, you know, each of those roundings are only going to add 0.00001 to the discrepancy. Yeah, so if I set epsilon to be 1 over the number of points, I'm only going to increase this discrepancy by 1. In fact, if our goal was square root n, I could have made epsilon, 1 over square root n instead. So this is a very minor point. Once you're sufficiently close to 1 or -1, that's good enough because you can just deterministically round after that. Okay. All right. So I think the first starting idea, and this goes back to Bonsall, is we won't try to color everything in one shot. We're going to try to kind of get half the colors. Right. So there's this idea of partial coloring. So okay. So the high level idea is we're going to identify some kind of fractional coloring, and it's going to have good discrepancy, right? So every set, will be at most squared n log n, or whatever our bound is. Okay, but I do want to make some progress towards getting a full coloring. So we will insist that any constant would have been fine, but at least half of the coordinates become tight. Okay, so I start at some fractional point. I start trying to make changes, and my goal is to just for half the vertices get to red or blue. Okay, within the discrepancy bound. Okay. So, okay. So how do we go from a partial coloring to a full coloring? The first round, you just do a fractional coloring and you get half the vertices to be tight, and you pay square root n, right? Now, if you can do this log n times and eventually get the number of colors down to 0. Okay. The only problem is that each time it looks like you're adding square root n discrepancy, so that you would pay square root n log n overall. The whole point is to avoid this log n factor. But maybe so the algorithm is kind of like that. Suppose I told you that are guaranteed to be a little bit more general. It will say that for any starting point, fractional starting point, I can gradually make it more integral so that half the coordinates become tight, and my discrepancy will be square root of number of vertices. Okay, so if I allow that, then how can I argue that just this kind of repeated thing will get me good discrepancy? So we have this partial coloring lemma, except I tell you that you'll get this guarantee no matter where you start. So let's just say m is equal to n, so you can ignore the log m over n. So I want to get square root n overall, but naively, if you repeat the partial coloring log n times, it looks like you pay square root n each time. I'm saying that's not quite the case, because one thing does help you. Okay, so the first iteration you pay square root n, and you color half the colors. And the algorithm is going to basically remove those vertices or just keep them frozen. They are red and blue forever. Okay, and then we'll just start the next round with the remaining n over 2 vertices at most that are still not frozen. They're between 1 minus epsilon and 1 plus epsilon. And then I do it again. Yeah, it was those n over 2 vertices. All right, and then half of those become frozen. Now I'm left with n over 4. Okay, and then the remaining n over 4 live ones will become the starting x0 wherever they left off. Okay, the first round you pay square root n discrepancy because there's n vertices. How much do you pay the second round? Square root n over 2. And how much do you pay the next round? Square root n over 4. So if you add all those up, what do you get? You guys are so exact. You get square root n, right? Because it's a geometrically decreasing sequence. So because the bound is square root n, where n is the number of points, but n is going down by half each time, your discrepancy you pay goes down by 1 over square root 2 each time. Now, it does help that things are kind of like concave because like square root of a plus b is less than equal to square root a plus square root b. So the individual discrepancies you're getting round by round will upper bound kind of the discrepancy of the whole thing. Okay. So yeah, so that's the you'll get geometrically decreasing thing. So you only pay, it'll be dominated by the first iteration. Okay, so that's why it suffices to just color half the vertices and pay square root n, as long as you can start from anywhere, because then you can pick up without incurring extra cost. Okay, good. So that's the idea. I just want to take my fractional point. You can imagine it starting at all zeros. That's the most natural point. But in the second iteration, it's starting in some arbitrary point. Yeah. We won't actually, at some level, we won't even notice x0 in the analysis. And you'll be like, oh, I guess it could have been anywhere. Okay. All right. So now we just want to figure out how to color half the points. All right. Good. So this is going to be some kind of random walk algorithm. And I'm going to use P to denote kind of the polytope I want to stay inside. So by polytope, I mean at some level, our point X, right? So at some level, we want to get to one of these corners where this is like 1 and -1 on each axis and stuff, right? This will be like 1, 1, 1. So we want to, and you start somewhere like in the middle, and you're trying to make it out to one of these integral corners. And meanwhile, all these sets are saying, okay, there's like certain walls. I don't quite know how to draw. I should know how to draw this, but this is saying like, okay, if you go beyond this point, the discrepancy is too high. If you go, too far, each of those lines are supposed to be kind of planes. And it's saying, okay, this is sort of the linear inequality that's imposed by the set, right? Oh, the sum of differences of the colors can't be bigger than square root n here and square root n here. So you're gonna have this high dimensional cube originally. This is the -1, 1 box. And then you're gonna have all these sides cutting off areas saying you can't go past this wall because then this set's discrepancy will get really bad. Right? Because discrepancy is two linear equations, right? Red minus blue is less than equal to square root n. And then blue minus red is less than equal to square root n. So these will just form some kind of diagonal looking thing on that hypercube. It's kind of hard to visualize anything, but that's what it is. But the point is that you're in some high dimensional space. It's impossible to imagine. It's very hard to work with algorithmically. But you do know all the sides are based on linear inequalities. Less than equal to 1, greater than equal to -1, and then sum is greater than equal to negative square root n, and sum is greater than equal to square root n for each set. Okay, so that's called a polytope. Anything with kind of sides like this. So P is going to be this kind of feasible polytope. So these are all the points in -1, 1 that satisfy the discrepancy bound for all of our sets. Okay, so that's we're going to try to take a random walk in it. We'll start at 0, 0 for the first iteration, and then we're going to kind of take a high dimensional random walk and try to argue that you actually make progress, but we'll always stay inside P. Okay, which obviously or not obviously, but the real critical part is making sure we don't violate the discrepancy of the sets. Okay, so how does this algorithm go? So we're going to take a random walk. All the points will be inside P by design. Okay, and and every step is going to be a Gaussian vector. Okay, so the first iteration, you're going to get a random Gaussian for every coordinate, and you'll be very small variance, 1 over poly n or something. So you take a tiny step. Okay, you take a tiny step, tiny step, tiny step. So initially, you're just doing a random Gaussian walk where each coordinate is a random Gaussian. So just a random Gaussian vector, and it's just moving completely randomly through the square. Okay. Now, of course, at some point, well, I don't know, I shouldn't say of course, but ever really. But as this walk moves around, it's going to run into some of these walls. And a coordinate may approach 1, or one of the sets may become kind of tight, right? They become dangerous. All right. Then you want to suggest that's when we start making some changes. Okay. The random walk will get dangerously close to some constraint, whether it's a coordinate approaching 1 or the discrepancy of a particular set approaching square root n. Okay. So what might I do to adjust my random walk in this situation? So let's say there's a set that's getting dangerous. I'm really close to square root n. I don't want to take another step that risks it. When you say take a step, do you mean like for every coordinate you sample Gaussian with the extra? Yeah, so every coordinate you sample Gaussian. And that gives you a vector in some direction, and you just go there. Yeah, so the random walk is going to go, it's going to move around. Okay. And you're kind of hoping that it will somehow run into a corner. That means, yeah. Okay. In general, things will kind of deviate away from the origin. It might go back from origin, but yeah. How do you calculate P? Well, okay, I can at least check if a point is in P. Is that okay? Oh, so we never quite construct these are like a big system of equations, and I'm just promising we'll stay in P. And okay, at the very least, do we agree that it's easy to check if my point X is in P? I check if all the coordinates between 1 and -1, I check the discrepancy of all the sets. So it's easy to check. And it's easy to find one point in P because X0 is already in P, which maybe is the origin for the first iteration. Just think of X0 as the origin, and in hindsight, you'd be like, oh, it could have been anywhere. Okay. So you start there, you get a point in P, and you know how to test your NP. And you can even check when you're getting close to one of the sides of P, right? You just look at all the sets and say, this set, my discrepancy is square root n minus 1. I should start being careful. Or square root n times 0.9999, right? And you start being careful. So you can kind of test and get some of the information you need. We'll never like physically create it. We'll never render it on a computer. High dimensional anyway. I don't know how you would. Right. So it's just math, imagination stuff. Okay. Yeah. So for example, okay, just one naive way to stay in P, right? Is I pick a random vector, just like no, every step is a random vector, and then I can calculate. Let's say I'm supposed to move like 5 inches or something, but I can calculate like as soon as you 1 inch in, you're going to run into one of these walls, right? So one natural thing is when I run into a wall, I just truncate the step or something, right? And every step I somehow kind of truncates things that go off in wrong directions and stuff. So what does that kind of yeah? So or maybe another question then is okay. So maybe that's another way to think of it. So another random algorithm would something be like I'm walking around and there's these walls that I can't cross. And I'm hoping to get to some of these corners or a point where half the coordinates are integral, right? So the question is, when you run into a wall, you should stop. You shouldn't go past the wall. But then how do I kind of sample my next direction, right? Because I want to sample a direction that somehow doesn't go into the wall. We can do some orthogonal projection type stuff because everything is a linear inequality. Okay. So that's what we're going to do. What we're going to do is we're always going to take a random space in a subspace, random step in a and I'll expand it out with details in a moment. But that subspace is always going to be chosen to avoid all the dangerously tight sets and the tight coordinates. Like coordinates is pretty straightforward, right? Like if my coordinate xi is already equal to 1, I just won't sample any Gaussians. That one's done, right? And the only question is, how do I do the equivalent thing for sets? Once a set is basically done, it's hit its discrepancy limit. How do I make sure that I don't add any more discrepancy in the next iteration to that set? But there may be lots of points in that set that still have partial coloring. So you do want to sample the underlying points, but you want to guarantee that set does not become worse. Yeah. Well, yeah, I think it's not too helpful to treat every iteration as x0 because x0 is really marking also when we make progress on half the vertices. Like it's really important that we're able to fully color and resolve half the points while paying squared n so that overall we get a full coloring. So I think we want to keep x0 fixed because that's the role it's playing in terms of kind of marking. Yeah, because you need that for the higher argument for going from partial to full. Okay, so yeah. Yeah, does it have to be zero mean? Can I add uh I could can I can I can I adjust the thing to kind of push away from the boundary? Like I don't know, two magnets that are both plus getting really close to each other or something? Some kind of barrier or something? Yeah. Yeah, exactly. So this orthogonalized idea. So what we're gonna do, yeah, so how we can come back to the two lemmas. So okay, so okay, so we'll say constraints tight, if you're within one minus epsilon, and I'll also say that a set is tight. I mean, a coordinate's tight and a set is tight if they're within one minus lambda minus epsilon and one minus epsilon. Okay. We'll do a Gaussian with standard deviation much smaller than the epsilon, so the odds of exceeding epsilon is very small. Okay, so this is like kind of being, one step away from the boundary. And okay, so the safe subspace, right? First of all, oh, I guess, yeah. So the safe subspace, right? I want to only look at directions where first all the coordinates that are tight, I don't do anything, right? And uh, for all the sets, I want to add nothing to discrepancy. Okay, so y is some fractional thing, but it should sum to zero for every tight set. All right. So yeah, that's what we'll do. How do you actually implement this? So let's say that you have a handful of tight sets and tight coordinates, and you want to take a random Gaussian from the safe subspace, so to speak. So first of all, do we feel okay about like the role of the safe subspace? You have some tight constraints, tight sets. If you work in the safe subspace, you won't change any of those sets and those coordinates anymore in terms of their measure. Okay, you're keeping everything zero there. Okay, so now the only question is, how do I get a vector from that space? Yeah. Yeah, so how do I see if, okay. All right, so how are we going to sample a Gaussian vector from this subspace? Okay, so it's gonna be said. Okay, so your approach was let me get a Gaussian to high dimensional space and subtract out the projection onto the subspace. I think that'll work. I'm actually gonna work from the opposite direction. So let's say that that YT has k dimensions. Okay, but I think this adds up to the same thing. Although I'm not 100%. We'll take any orthonormal basis of our subspace, right? So some principal axis that's good for our subspace. Remember, Gaussians are rotationally invariant, so it doesn't really matter what axis you pick. And then, you have some matrix that looks like this. And now if I sample one Gaussian for every of those basis vectors, right? And then I return UG or something, this is a random Gaussian in that subspace, right? Any basis in that subspace would have been fine because everything's rotationally invariant for a Gaussian. Okay? Maybe that'll be a nice homework problem to show this is equivalent. It's got to be equivalent to picking. Oh, yeah. Okay. Actually, maybe I'll give it now because I see how to do it. Okay. So are we okay with this algorithm? So I want to get a random Gaussian from this k-dimensional subspace, pick any basis, get k Gaussian random variables, and use that kind of in terms of that basis. Okay. The other suggestion was, okay, so I have some subspace, right? So I can first sample a Gaussian Rn into a big space and then remove the projection from that subspace, right? So that subspace is like here, and the full space looks like here. You pick a Gaussian like out here. You subtract this part, so then you end up just on this axis, right? If it was two-dimensional. Okay, so I think you can argue slickly that this will be the exact same thing. But does anyone see like a nice compact? First of all, I feel like it's kind of believable because these things seem to work out with Gaussians. But can anyone come up with like a concise explanation? Do you have one? I mean, it was your algorithm. I think there's at least one kind of trick way that we can all see they're the same. Should I give a hint? Okay, rotational invariant would have been my hint. So how do you use rotational invariance to make it like really obvious these are the same? Yeah. But first of all, the word unitary is ridiculous. Just rotate the space. You don't unit. Yeah, you don't like one in common discussion where you ever use the unitary is not even a verb. You, anyway, that's like classic like nonsense. So okay, so we imagine like Rn as like n coordinates, right? Like this. Now everything is rotationally invariant. So I can just imagine that my subspace YT is, I don't know, the first four coordinates, right? And if you sampled a random Gaussian for each one and you just ignored these two, that's the same as just sampling Gaussians from these four, which is what the other algorithm is doing. Okay. All right. That's okay. So rotational invariance, just pick the rotation to make your argument very convenient, and then it's kind of straightforward. Yeah, it takes some getting used to this whole like, oh, rotational invariance solves all my problems, but then once you get used to it. Okay, good. All right, so then that's just the algorithm. So you can just sample from the safe subspace. This is a very natural algorithm in some sense, right? You're taking a random walk. In general, like a random walk will kind of go, you can't control it, but it's going to move away from 0, 0. It's going to it's going to gradually increase in magnitude, go off in some direction, right? And uh, every time you run into a wall, you just walk along that wall, therefore, henceforth. I mean, that's effectively what you do when you make sure when you remove that component, right? You make sure that you don't make any progress in whatever perpendicular direction of the wall, which means you're going to move along the wall for the rest of the algorithm. So you're just trying to get to certain points in this big polytope. You take a random walk, you run into the wall, you don't go past the wall, you just go along the wall. That's expressed by this safe subspace. Okay. All right. I mean, high dimensional stuff is always hard to visualize, but that's exactly what's going on. All right. Okay, so two facts we're going to use about Gaussians. Okay, so this one you already know. which is just if y has standard deviation sigma, okay, the odds of the absolute value of y going at least 10 sigma is e to the negative 10 squared. 20 sigma e to the negative 20 squared. Okay. Uh, yeah, I think we might have seen it more in this form in the past with squared on both sides or everywhere. Same thing. Okay. Now, okay, our walks will be, well, I guess once you rotate, it's not so different. Well, okay, yeah. So it depends on various perspectives, but okay. So at some level, the first step is going to clearly be Gaussian, but once you start running into walls, at least depending on your direction, it's not going to be Gaussian in exactly the same way. So this form will be kind of convenient. Okay. So imagine I have a bunch of random variables, one coming after another. And the first one's Gaussian. The second one, conditional on the first, is a Gaussian of some standard deviation. So they're all going to be Gaussians, but you're just promised that they might change. Like depending on your first three steps, your fourth one might be different, but you're promised that the standard deviation is still at most one. Okay, so you're always taking kind of Gaussian steps. You're adding on Gaussians, but they might be smaller, so to speak, if you're measuring the size of a Gaussian by a standard deviation. Okay, but they're not fully independent. Your first five steps may lower the standard deviation of your six. And that's going to kind of happen to us because, yeah, we're going to run into these walls and stuff. Okay. So like the x1 coordinate, random Gaussian, random Gaussian, random Gaussian, but then you get some constraint that's kind of biasing you or it's kind of dampening you a little bit. And that's going to effectively reduce the standard deviation in the x1 direction. So now the x1 Gaussians are not quite the full standard one deviation Gaussian. They're a little bit smaller. Okay. Now, from the perspective of, what are the odds that I go way past the standard deviation of like one, you know, making the Gaussian smaller shouldn't really hurt you, but it is a little funky because you can't just say they're independent anymore. Okay. But morally, you're thinking like, this shouldn't be that big a deal. And that's basically what this is saying, right? So if these were independent, then the second bound, which is, oh, yeah, if these were independent, this would just be a sum of Gaussians, right? This would be some Gaussian, and there's t of them. So the standard deviation just goes up by t or something, right? And then this second bound would just be the first bound if they were independent. They're not quite independent, but the way they're not independent is kind of more in our favor. Like they kind of get dampened possibly over time. So you can basically repeat the same proof as part one, as part two. You just have to carefully do a little conditioning along the way, and you end up with basically the same conclusion. Okay. So in our analysis, because the random walk does get altered by some of these sides that we run into, it's not like every step in every direction is a unit Gaussian. But it's some Gaussian with standard deviation at most one we'll see. And so you'll still be able to apply certain concentration when the time when the time comes up. Yeah. Okay, so the risk is you get pinched in a corner, right? The risk is you run into too many tight sets before you're anywhere near. You get n tight sets before you get any fully colored points. So the surprising thing is that this algorithm should be able to color half the points before it kind of freezes up completely from tight sets. That's going to be the race that we're analyzing. Okay, and it's going to have a lot to do with actually these lemmas here. Yeah, that's exactly the risk we're trying to avoid, right? Because of course the algorithm is conservative. It makes sense. You run into a wall, don't go past that wall. Now, but the problem is we want to get to one of these particular corners where the vertices are colored, and it's not even clear. I mean, yeah, the walls might get in the way. I guess Spencer's original mathematical result ensures there does exist corners that are not blocked off by walls, right? But still finding it is a major issue. Okay. All right. So that's that. And yeah, so we're going to always work in a safe subspace. And the real crux is to say we're going to color half the points before we get locked down too much. Okay, good. All right. The intuition is strong. The force is with you. All right. So here's a very small lemma. So u is that rotation vector. Okay. This is pretty easy, but okay. It's just saying that if you take u transpose on a vector, the length won't increase. Why? What does u taking u transpose do? It's really the orthonormal projection. So, or is it orthogonal? No, it's a projection onto a space, right? Yeah. So u transpose is going to take your vector and project it onto the space, right? Because for each of your basis vectors, it's going to do a dot product with the basis. Okay, so it's just going to project onto your space. Yeah, so there's lots of like easy proofs. One is always projecting onto a subspace, right? So in other words, once you rotate it, it's only keeping the first 5 out of 20 coordinates, right? And if you're keeping some coordinates and dropping the rest, then the length isn't going to go up because you're just dropping some coordinates, right? So it's really helpful that the norm is also rotationally invariant, right? So just pick a rotation until it's convenient, and then you're just dropping coordinates. Right. Yeah, so one way to, once you rotate, you can think of U as just being the identity matrix on the first k coordinates, whatever the dimension of U is, and dropping the rest. Then you can directly verify. Okay, so I think it's really, I think one thing that makes the results sort of counterintuitive is that because we're so focused on these individual vertices going from -1 to 1, that makes us super biased to the standard basis, the natural basis, which is each vertex is a basis, right? But the walk is really always living in this subspace where it's being careful about all the tight constraints. So I think that the fact that we're so obsessed with the -1, 1 and always biased, it makes us forget that things are rotationally invariant and all the proofs are actually easy. Okay, because you can just rotate, but we kind of resist rotating because we're also kind of preoccupied with those n particular coordinates getting to -1 and 1. At least that was my sense when I reviewed the notes yesterday. I was like, hey, this isn't so hard. Okay. I remember when I was your age or probably older, thinking this is like the hardest ever. Okay, here's another one. Um, so for any particular vector v, imagine v being, for example, the indicator vector of a set, right? So UG, so you sample a random Gaussian plus or minus values, you send it through U, right? Because you're doing this random Gaussian from a subspace. And then projecting onto V is how much damage you do to the V constraint, the constraint corresponding to V. So the claim is that this is also a Gaussian. Why? You're like all about the hand waving, like literally hand wave. It's a question from the instructor. Not how it works. Yeah. Uh-huh. Yeah. Right. Okay. Yeah. Here, that's a better way to do this. The clumsy way to do it, okay, is you can just transpose it first. But the real point is that this is a Gaussian, right? And it's a sum of Gaussians. And we know some of Gaussians are like the world's nicest thing, right? So a sum of Gaussian is a Gaussian. The variance will be the kind of the Euclidean norm of the coefficients. Okay. So that means you're always taking Gaussians in any particular direction as well. So that's kind of nice. The variance may change, right? Because UTV is going to decrease the variance from just V down to the length of UTV. So the variance is going down in particular directions, but you're still taking Gaussian steps in every possible direction. Okay. All right. So the algorithm is for a small step size. So you sample a Gaussian. I guess I'm treating G as a normal Gaussian, but then you're dampening it by some small step size delta. That's like the same as taking a Gaussian with variance delta squared. And right, where the columns are orthonormal and they're the basis, and we're going to make delta so small that you'll almost never take a step size larger than epsilon. Okay, very high probability. Okay. Is the inner product of two Gaussians Gaussian? No. What we did was we showed that the length of a Gaussian vector is super well concentrated. That was basically the Johnson-Lindenstrass proof. But that's the dot product of a Gaussian with itself in particular. And then doing the cross product stuff, I mean, two different Gaussians is implicitly maybe very similar to your homework, or it gets closer to your homework, or you're trying to show some kind of concentration of dot product, but you get some weird additive bound. Okay. All right. So I think here's the basic claim. Oh, this one's not so bad. The claim is that if one point is in your polytope, the next step will also be in your polytope with high probability. Why? Well, you take a big step, right? I mean, each time you're taking a step of some fixed size, delta times the standard Gaussian. So how do I make sure I never leave the polytope? So you're worried about leaping over a wall, right? You're hand waving. Okay, so once they're tight, you won't break it. But what if they're not tight? Yeah. Yeah, because we set delta to be small enough, right? So the tight variables are all fixed. The loose ones, they have epsilon slack. And we're going to set delta to be much smaller than the epsilon. Okay, so our variance for in a particular like direction of a set will be delta squared size of S squared or something, right? S has a most n elements in it. Delta is epsilon over poly mn. So the variance is like epsilon squared over poly mn. The odds of the magnitude of this thing being bigger than epsilon then is super duper small. Okay, so that's all. So delta is small relative to epsilon. Epsilon is small enough that you can deterministically round at the end. You don't have to worry about it. But delta is even smaller, so you basically will never take a step size of larger than epsilon. So that buffer will be good enough. Okay, so that's not too bad. I should note that this what we just analyzed also implies that the expected value of the magnitude is at most n. Let me explain. If I look at a particular coordinate xti squared, right? If it's tight, it'll be less than, if it's close to 1 minus epsilon. Well, okay, so with high probability, it's not quite follow that with high, from high probability that you get is less than equal to 1, right? Because it still be maybe super big with super small probability. But at some level, like right before the 1 minus epsilon, before it becomes tight, you probably won't go past 1. And the odds of getting to 2 is just dropping down exponentially. Getting to 3 is dropping down super exponentially, stuff like this. So the same kind of calculations, but rearranged a little differently, will show that for every coordinate, the expected value is at most 1 in magnitude, or between negative. Yeah, the absolute value of expected coordinate is that, or the expected value of every coordinate squared is at most 1. And if I sum up over all the coordinates, it'll be at most 1. This is sort of intuitive, given that it's going to be in the box as high probability, which means the magnitude is at most n. But to do it properly, the calculations you have to doesn't immediately follow. Yeah, unless you know a little more about the high probability stuff. Okay. All right. Good. So, okay. So by the union bound, we'll only do this for a polynomial number of steps. All your points will stay inside P. Okay. And you always have this thing where the expected magnitude is at most n. You expect to stay in the hypercube. Kind of that's sort of not surprising. Okay. But that small detail will play a role later. Okay. Good. So this is all the relatively light stuff. Now things will start getting a little more interesting. Okay. So we have this random walk. It's always doing the safe step thing. And all we've kind of done is address, why the padding is there, the epsilon is there, and why we'll really stay in P, minor correctness stuff. Okay. Now, the real goal is to show that half of the coordinates at the end, after some number of iterations, capital T, which will be roughly 1 over delta squared or something, will be tight. Okay, so that's what we want to show. Uh, First of all, any intuition? So maybe one thing I should point out. So let's look at a particular coordinate. The first coordinate, right? And imagine there was no freezing or anything going. You're just summing a Gaussian, summing a Gaussian, summing a Gaussian, right? So each Gaussian would have variance like delta squared. Okay, and you take like t of them, roughly 1/delta squared steps. So I take I take 1/delta squared. That means that my first coordinate is the sum of these t Gaussians. And so what do I expect? So the whole thing becomes like a standard Gaussian of variance one or something, right? Because each one has variance delta squared. I take 1/delta squared steps. So overall, I get variance one. Okay, that's if I didn't do any freezing. And that means with constant probability, it'll be at least one or negative one, right? Because with constant probability, you're within a standard deviation. With constant probability, you're at least a standard deviation. So with constant probability, you get at least one or negative one. So if I didn't have any sets involving coordinate one, it only gets frozen once it gets to one or negative one. So, okay, let's say I take 10 delta squared steps instead of just delta squared steps. Then I either reach one or negative one, or I've somehow taken, I have some random variable that's probably one or negative one, right? So it's sort of like, okay, if it was unobstructed, then it should get to one or negative one. And the primary obstruction is it'll get to one, negative one, and get frozen. So that's like the high level intuition. If you keep summing Gaussians, you do expect some even though the average is always zero. But you expect it, the constant fraction of time to kind of get fairly far away from zero. So if you didn't have to worry about sets at all, you would reach a corner, is a good point to make. Okay. The only question is, can you get there fast enough? Because as you start freezing sets, each coordinates Gaussian kind of gets smaller in magnitude, right? Because this set's saying, you can't be that aggressive in this direction because of this and that. Each of those subspace, projections is kind of dampening the magnitude of your step, so to speak. So yeah, so we're going to try to argue that, you know, as long as less than half the coordinates are tight, you're still adding a lot of randomness, a lot of Gaussian stuff, and the remaining coordinates are still going to make a lot of progress. And you always know the expectation this magnitude can't get bigger than n. Okay, so we want to show that as long as this is still like an n over two-dimensional Gaussian getting added each iteration, I'm still growing like delta squared over two, delta squared n over two or something. Each coordinate grows on average by delta squared because I'm still kind of adding n over two-dimensional Gaussian, right? So in the safe subspace, I'm getting a full 1 unit of variance every time, or delta squared units of variance every time. And so as long as almost half the coordinates are tight, and let's say very few of the sets are tight, then I'm hoping this is still growing at a fairly fast rate. And meanwhile, the expected value is always bounded by n. So I shouldn't be able to exceed n. So in other words, as long as I'm not done, I should be growing so fast that I have to be done soon. That's sort of how we're going to try to sandwich and show that we win. Okay, but a key point is showing that not many sets are too big. Okay, so let me make this point clear. So the claim is that so that's how much the magnitude of our vector increases in one iteration, right? Then the length squared of xt minus length squared of xt minus 1. And we know once we get to n, all the points must be integral because it's still going to be inside negative 1, 1 with high probability. Okay, so once I get to n, I'm done. And so this is saying that I'm making, delta squared comes from taking a step size of delta, but it's saying I'm making progress in proportion to the dimensionality of the safe subspace. Okay, so as long as I still am effectively generating n over two Gaussians, I'm still increasing I might not be increasing by a full delta squared n like I would in the first iteration when nothing's frozen, but I'm still increasing by delta squared n over two as long as I still have n over two dimensions in my subspace. Okay, so like, for example, all that will imply, I messed that up, that's okay. An expectation, okay, this would be expected value. N is always at least expected magnitude of the last vector, and I can telescope that into all the individual increases, right? And the claim says that this will be at least the sum of the dimensions. and I'm dropping off the negative term from x0, okay, which would only help us. And uh okay, there should be a plus because of the telescope. Okay, it doesn't matter. Yeah, that doesn't hurt. And one thing I want to point out is that you could just write this in terms of that's not correct, but you could just write this in terms of the last dimensional subspace. Okay, so here, I'm making progress each iteration based on the dimension of the subspace at that iteration, and I'm saying that's at least the total number of iterations times the dimension of the final one. Why? It's the smallest one. So our safe subspace just gets smaller as I add more and more constraints. It doesn't always get smaller. We could be adding constraints that are like redundant. I guess you wouldn't add them because they wouldn't make progress. But anyway, okay. Okay, so at some level, as long as I can show that the dimension at the end is n over 4, n over 10, then taking t to be 10 delta squared, 10 over delta squared, I'll be happy. All right, so that's where it's going to fit in. Now let's try to show that. Okay, so why is this true? Why is my increase, my progress, proportional to the dimensionality of the subspace I'm sampling from? Yeah. I mean, I think we all agree with the intuition. So how do we articulate this cleanly? It's a bit of a technical statement, right? It feels mathy, but there is a clean explanation. You're doing this thing where you're like, I'm not really raising my hand. So why? There is a clean explanation. Yeah. Yeah, I mean, you can kind of deduce that pattern matches. I feel like you're missing just one word to really concretely. You could kind of crunch the calculations that way, but you wouldn't find it as compelling. There's just one buzzword: rotationally invariant. Like if yt was just the first 10 dimensions and it was just delta squared times 10, would that be completely obvious? So let's say that the safe subspace was just the first 10 coordinates. All the other coordinates were stuck. Then you're just adding a standard Gaussian to each of the first 10 coordinates, right? So, okay, each one you get delta squared, you get 10 times delta squared. Now, this is not exactly the first 10 coordinates because it's some subspace, but it is because everything is rotationally invariant. The norms are rotationally invariant. The Gaussian vectors are rotationally invariant. It could have been the first 10 vectors that are your subspace. You don't really care because we're just measuring the overall magnitude of the vector. We don't care about the particular coordinates in this statement. Okay, so roof. Okay. Uh, okay, that's never happened before. I mean, I've had proof on many slides, and okay, that could be a joke. Okay, something about a dog. All right, so up to rotation, that difference is just some k-dimensional Gaussian, with some variance depending on your step size, and right. So this is a sum of k Gaussian squared. Yeah, so you're expecting k, delta squared is the expected value of that Gaussian squared. Yeah, so each one's contributing delta. Okay, it's very nice, right? Like, in fact, I think an earlier version of slides did do the calculations slowly. I mean, that's completely unnecessary. Just rotate. What the? Okay. All right. So now we're going to start putting things together. Okay. So all right. So now we know that n is at least delta squared times t times the last dimension. Okay. And now I want to start doing something like this. At some level, n is kind of coming from here. But I want to say that the expected number of tight coordinates is at least roughly n, because delta squared over t is going to be some small constant, okay? Because 10 will be like, say, 100 over delta squared. So this is basically 1. It's basically n minus the number of tight sets. And I claim that's going to kind of follow from our previous lemma, especially if you ignore the delta squared t. But the question is why? So what is the bound for the dimension of our safe space? N minus number of tight sets. Not done yet. Minus number of tight coordinates, because we also freeze the tight coordinates. Okay. So at some level, let's say the number of tight sets is not very big. Then this is just n minus the number of tight coordinates. And if you have half of the coordinates tight, you're already done. And if you have much less than half, then this is still very big. That's really what's going on. N minus number of tight sets, tight coordinates. I think just up to rearrangement of terms. Is it here? Yeah. So you have this from before, and you just expand that out, and you just rearrange things, and then you get that bound. Okay. So what does that mean? So at some level, if there was no tight sets, and you're only worried about tight coordinates, then it would be kind of straightforward, right? Because every coordinate is making progress roughly proportional to delta squared, unless it's tight, and in which case you're happy. Okay. The only thing deterring you is the tight sets, and they're kind of dampening the overall coordinate progress in the aggregate, right? Because each tight set decreases the dimension of the safe subspace, your sampling subspace by 1. So now instead of getting n delta squared in magnitude each iteration, you're getting n minus 1, and then n minus 2, and then n minus 3 as you add more and more tight sets. Okay, so that's fine. So now all that's left is bounding the number of tight sets. All right, so the claim is that the expected number of tight sets is like n over 4, n over 8. Any constant is fine. Okay, nothing here. All right. Any ideas why it should be small? All right. Well, here's the rhetorical next question. All right. Let's look at a particular fixed set. Okay. And now I'm looking at the difference in discrepancy from one iteration to the next, right? So this is what is this as a vector? On average, it's 0. This is not necessarily a tight set. This is just any set. On average, it's all 0. I think. I'm actually a little confused once you take the projections. I feel like it's probably 0, but it doesn't matter. But what is this as a vector, as a random thingy? Yeah. So what is it? What is it distributed as? Okay. So if I wrote this thing right, this is going to be uh you know you sample a Gaussian from your subspace, and then you add up things based on SI, right? So it's a sum of Gaussians. Each of these discrepancies are a sum of Gaussians. And what will sigma squared be? What will be the variance of one of these steps? You want to upper bound it. So this is the kind of discrepancy added to set SI. What? Well, how many elements are in SI? At most n or something? So, okay. So the variance could be at most delta squared size of SI. It could be a little smaller because the subspace will only make it better. Because that would be effectively the magnitude of the corresponding all ones vector, right? Because you're really interesting, you can think of summing over S as taking the dot product was the ones vector over S. Okay, so it's at most delta squared n. Yeah. All throughout the algorithm, it's at most delta squared. It might get smaller as things get frozen, but it's at most delta squared n. And okay, so we have that. And now, okay, so the probability that this set is tight is that the probability that the sum of all these things, exceeds lambda minus epsilon, right? Okay, and this is going to be where we bring in that effectively as if they were independent, but it's conditional. Okay, because the variance only goes down, but it's always at most delta squared n. If you plug in chug, you're going to get lambda minus epsilon squared over 2t delta squared n. The delta squared n is coming from the variance, and t is coming from the total number. Okay, and because you're really, it's really how many units of variance. So it's lambda minus epsilon times delta squared n divided by delta squared n kind of thing. Okay, and when you start plugging in, t is big O of 1 over delta squared, then you get something like n in the denominator, n in the numerator. I mean, your discrepancy bound in the numerator squared. Yeah, n log, n. At this point in the class, I've given up even writing C for constant, and I just put a big omega there. You can make as big a constant as you want. Okay, and this is, say n over 8m if there's an 8 there. Okay, so the log m over n will give you something that lets you union bound over all the sets. Okay, so what's the expected number of tight sets? There's m sets total. N over 8. Good. Anything here? No. All right. So now what's the expected number of tight coordinates? N over 8 magically became n over 4, but it'll still be okay. It's still true. Hmm? It's the expected number of tight coordinates. Well, we have 1 minus delta, so this is at least 8 over, so this is 1/8, 7/8, minus 1/4. Um, I don't know. Maybe this should have been n over 8. Okay. All right. Okay, so it's at least 3 n over 4. Now you want to argue that you get at least n over 2 half the time. How? Okay, so we're going to use Markovs. So what are we applying Markovs to? The number of not tight vertices is that most n over 4. With constant probability, there's less than n over 2 not tight vertices. Okay. All right, so that's the whole algorithm. We completed the whole proof. Okay, so at one level, it might feel like we did a lot of calculations, but at another level, almost like once you just rotate this space, everything became very easy, and it's almost like the Johnson-Lindner-Strauss. Wow, okay, rotational invariance does quite a lot for you. In this case, there's always enough leftover kind of randomness to keep making sure you deviate at a pace, move away from all zeros at a rate that's fast enough to get you to an integral point, even as you're freezing things up, right? So somehow we can barely kind of thread the needle. While I'm still freezing some tight sets, there's still enough randomness, but the rate is fast enough that you will actually make progress and get this kind of magical coloring. Okay, so this is like some kind of like very sophisticated rounding technique is maybe one way to think about this. Okay, so that's it. That's this famous discrepancy result. Just high dimensional Gaussians on steroids. Okay, thank you.